Now, we've talked a little bit so far about some of the key points in energetics involving chemical change. So those energetics associated with chemical reactions. Well, those aren't the only types of changes we can observe changes in the energetics. And so physical change, chemical change, nuclear change, all associated with energy release or energy absorption. So I just want to quickly point out some of the differences, the main differences you'll see when we compare these three different types of chemical changes, so to speak. So to start with, I'm just going to get you to watch three short little videos to sort of give you a bit of an idea what sort of energetics we're looking at here. So have a quick watch of these videos.
Sedan was detonated at 10 a.m., July 6, 1962. This is a view taken from the top of a 1,500-foot tower, located 6 miles from ground zero. This close-up view was taken from a ground station 3 miles from ground zero. The dome rose to a height of 290 feet before it vented at 3 seconds. The base surge seen forming here continued to grow until it covered an area about 5 miles in diameter. The main cloud rose to a height of 12,000 feet above the desert floor.
Okay, so not really too hard to see which one of those, physical, chemical, or nuclear, is associated with the largest change in energetics. So let's just quickly summarize those three different changes. So a physical change is associated with smallest amount of energy change of the three, and that's because if you think about what a physical change is, it's just a breaking of those weak intermolecular forces. So hydrogen bonds, dipole-dipole forces, or dispersion forces. Now hydrogen bonds can be quite strong, as you've seen with water. You do have to add quite a bit of energy to water, but that said, the breaking of them is not as hard as, say, breaking a typical chemical bond, a covalent or ionic bond. So if we look here at this at delta H, that's a change in enthalpy. So a phase change for water, one phase change is going from the liquid to the solid state. And because you're going for a higher energy state to a lower energy state, that's an exothermic process. And so we release 6.03 kilojoules. So that's not a large amount of energy released in going from liquid to solid, but it's energy released nonetheless. Well, let's have a look at a chemical change. So you've seen this reaction before, the thermite reaction. Aluminum plus iron 3 oxide yields iron plus aluminum oxide. It's quite an exothermic reaction, as you've seen and felt. If you're standing close enough, you feel quite a blast of heat coming your way. And the delta H for that, again, it's an exothermic process, 850 kilojoules, so about 2 orders of magnitude greater than a phase change for water. And so quite a bit more energy associated with a chemical change. Finally, a nuclear change. This comes about due to a change in the nucleus. There's a huge amount of energy stored in the nucleus of atoms, and so if you can get that energy released, well, you're looking at the release of a huge amount of energy. So again, a typical fusion reaction, as shown here, yielding a helium isotope, so two isotopes of hydrogen yielding a helium isotope, the delta H, the energy released there, 530 times 10 to the 6 kilojoules per mole. That's 6 orders of magnitude greater than the energy released in the thermite reaction. So nuclear change, energetics involved with nuclear reactions is tremendous. And so, not surprisingly, we see a much larger release of energy. And so you do have to have a bit of a handle on those 3 different changes associated with physical, chemical, or nuclear change, and the energetics associated with them. And that concludes this video.